Myself Karthikeyan, I am from CSCC section. Today my video assignment topic is about connected and bi-connected components. In that introduction to graph connectivity, a graph consists of vertices as nodes and edges as connections. Connectivity measures how strongly vertices are linked. A graph can be connected or disconnected. There are two components, connected components and biconnected components. In connected components, group of vertices linked by paths. In biconnected component, stronger form of connectivity. Understanding these helps in networking and data analysis. Connected components definition. Connected component is a maximal set of vertices. Every vertex in a component is reachable from others. No vertex in one component connects another. A graph with one component is called connected graph, used in clustering and social network analysis. Example 1, 2, 3 and 4, 5 are two connected graphs. Example of connected components are component 1 is connected to both 2 and 4 and 2 is connected to 3. In component 2, the 6 is only connected through the 7. Connected components algorithm. Common method. Depth first search. Starts DFS from a unvisited node. Visit all reachable vertices. One component. Repeat for remaining unvisited vertices. Count of DFS runs equals to number of components. Time complexity O of vertices plus edges. Code for DFS is DFS of vertices. Mark V as visited for each vertex U adjacent to V. If U is not visited, DFS of U. Biconnected components definition. A biconnected component BCC is a maximal subgraph. Removal of any single vertex does not disconnect it. It ensures strongly connectivity among nodes. No articulation points inside a BCC. Helps in analyzing reliable and networks. Every graph can be decomposed into several BCCs. Here example 1 is connected through 2, 2, 3 and 4 and those are directly connected to 5 and 5 is connected to 6. 6 is connected to the both 7 and 8. Articulation point. Vertex whose removal disconnects the graph is called articulation point. It increases the number of connected components. Found DFS tree properties critical in networking design and fault tolerance. Example in graph 1, 2, 3 with the 2 linked to 4. Vertex 2 is articulation point. Identifying them helps avoid single point failures. Here is one example. Here 5 and 6 are the articulation points in biconnected graph. Tarzan's algorithm for BCC, developed by Robert Tarzan, uses DFS traversal. Uses two arrays, disk of and low of, maintains a stack of edges during DFS, finds articulation points and BCCs efficiently. Condition: if low of V is greater than or equal to disk of U. U is articulation point. Time complexity O of vertices plus edges suitable for large graph. Example vertices 1, 2, 3, 4, 5. Edges are 1, 2, 1, 2, 2, 2, 2, 3, 3, 2, 1, 3, 2, 4, and 4, 2, 5. Biconnected components are 1, 2, 3 and second one is 3, 4, 5. Comparison between connected and biconnected components. In connected component, it is based on vertex connectivity. In biconnected component, it is based on edge and vertex connectivity. Connected easy. performed by basic linking. Biconnected is used by strong linking. Connected graphs have no articulation points, and biconnected graphs have articulation points. Algorithms DFS are connected, Tarzan for biconnected. Applications network reliability used to identify critical nodes or links whose removal disconnects a network. Circuit design helps in finding weak points or redundant paths in electronic circuit layouts. Social networks detects tightly connected communities or groups where every member is linked via multiple paths. Database system ensures fault tolerance by alternate routes in different in distributed data systems. Graph visualization simplifies large graphs by collapsing each biconnected component into a single node. Software engineering used in analyzing module dependencies avoids single point failure software architecture. Conclusion: biconnected components provide a heavy way to measure graph roughness. They help detect articulation points which are weak spots in connectivity. Tarzan's algorithm finds BCC's efficiency in space and time complexity. Understanding BCC's aids is improving network design and fault tolerance. There are fundamental in graph theory, bridging theory, and real world applications. In short, BCCs reveal how strongly parts of network tied together. Thank you.